Hello, everyone, and welcome to another episode of our MAE speaker series. Today, we are joined by Dr. Dean Kontinos. Dr. Kontinos earned his Bachelor of Science degree in Aerospace Engineering right here at UF, so go Gators, of course. And then he went on to earn his Master's and PhD in Aerospace Engineering at North Carolina State University. Dr. Kontinos is Chief Engineer of the NASA Ames Research Center in Mountain View, California. His responsibilities encompass independent technical authority on spaceflight and critical facility projects at Ames, ensuring the integrity of technical decision-making, approving waivers, resolving anomalies, and promoting best engineering practices. Previously, he was chief of the Entry Systems and Technology Division, acting as a focal point for Ames Entry Systems competency. With a wide scope of management experience involving hypersonic fluid and thermal protection system, to design of planetary probes and landers, to engineering of human-rated systems, along with provision of flight instrumentation. Other experiences include NASA Engineering and Safety Center Chief Engineer at Ames and Technical Integration Manager for the Fundamental Aeronautics Program on detail to NASA headquarters, as well as Chief of the Aerothermodynamics branch. We are so delighted to have Dr. Kontinos here with us today to discuss his experiences and insights. And with that, I will hand it over to you, Dr. Kontinos, to begin your presentation and discussion.
Hi, everybody. My name is Dean Kontinos, Chief Engineer at Ames Research Center. And what I thought I would do is introduce you to Ames Research Center and describe how I got there. I think many of us in NASA who work in NASA often reflect and ask ourselves, man, how did we get here? You know, working for NASA is pretty cool. You know, how do you end up there? And I'll tell you my pathway and also tell you about the center and we'll go from there. All right, so I'll start with myself. I'm moved to Florida in 1976 during the big migration there from the Northeast. And I moved to Fort Myers and I went to UF from 82 through 88. And then those of you quick in math says, well, that took 6 years for undergraduate. But what I did is I had co-opted with General Dynamics in Fort Worth. Right now it's a Lockheed plant producing F-35s, but back when I was there, it was producing F-16s. And so I'd work a semester and then go to school for a semester. And so it kind of stretched out my undergraduate. But I got to tell you, it was very much worthwhile. For a couple reasons. I think reason number one, it gave you a sense of what an engineering job is like. And speaking for myself, you get into engineering in school, but you don't really know sometimes what an engineering job consists of. And you kind of imagine it, but you don't really know. And working, going to school at the same time, kind of gives you a sense of purpose and appreciation for what you're headed into. It also helped my grades. I don't know. I was able to connect what was happening on the job with the schoolwork. At the time I was at UF, and maybe the professors here can relate to this, it was a period in academia where it was very much engineering sciences oriented. And so that meant a lot of math and a lot of theory, you know, as opposed to what I think today, it's shifted back more toward practical application. You do a lot of projects, a lot of hands-on kind of work is my understanding. But when I went through, it was a lot of theory and being on the job in a co-op situation was very good because you connected the theory to actual practice. Co-oping was very valuable because I took that engineering job at the F-16 plant and I realized that's not what I wanted to do. So I went back to graduate school and I went to NC State to continue on with studies. And how I got to NC State was pretty interesting too. And without going into a lot of detail, at the end of the day, you know, ACC basketball brought me there. I thought that would be a good way to, while going through graduate school, be able to watch, you know, Duke and Carolina and NC State play. I was funded through a NASA Hypersonics training grant. And that then provided an opportunity, because it was NASA funded, to intern at a NASA field center in the summer times. And most people, being in Raleigh and NC State, went to Langley Research Center in Virginia. That was a strong connection. I chose Ames in California because honestly, I had never been to California before. So I said, why not? So these decisions that I've made that, on some kind of crazy rationale really ended up shaping my life. So I ended up at Ames just because I'd never been to California. So I was a hypersonic CFD researcher at Ames. I then became the chief of the aerothermodynamics branch, which is, again, it's the application of CFD to entry spacecraft and determining through calculations and also experiment how hot basically the thing gets. I then went to NASA headquarters and spent a year there working at the headquarters level, appreciating how programs are put together and how the agency functions. Went back to Ames, became a division chief for entry systems, which is kind of the whole process of how to get a capsule from orbit down to the ground. And now I'm currently chief engineer. I'll explain at the end what a chief engineer does within the context of, you never really know where your career is going to go. Leave yourself open to opportunity and see where it takes you. Also, I just as a comment, if you look through here, I've moved around a lot, and I read somewhere that one of the key, the central correlating parameter to a successful career, not necessarily a successful life, but a successful career, is people move and they follow the job. And that certainly bears out in my experience. So let me tell you about NASA. NASA has some primary missions, and I think we all appreciate it, but this slide kind of describes the different enterprises. There's Earth science, there is aeronautics, there's human space flight, there's also solar system exploration, and space technology development. And the agency is structured around these enterprises. NASA has 10 field centers. I think, I'm sure people in Florida are very familiar with Kennedy, and, Johnson Space Center is very well known. But people probably aren't aware of all 10 centers. So I'll just kind of take a little tour. Kennedy is space operations launching. Langley Research Center in Virginia, Glenn Research Center in Cleveland, and Ames Research Center in California were originally NACA field centers, National Advisory Committee on Aeronautics. So they actually predate NASA. NASA is an amalgam of the NACA centers, the research areas, and human spaceflight activities. Goddard Space Flight Center does a lot of Earth science satellites, and that's in Maryland, outside of DC. Marshall Space Flight Center does rocketry. They're in Huntsville, Alabama. Stennis Space Center is primarily a rocket test facility, and that's in Mississippi. And then Armstrong Flight Research Center, shares a desert, basically, a dry lake bed with Edwards Air Force Base. And that's the home of the X-1 testing, right stuff, all those things happening in the desert. And then Ames is up in the California Bay Area. And so I'll show you where Ames is. I kind of plot this graphic. The graphic's not geometrically, it's geometrically stretched kind of in the horizontal axis. But that's the San Francisco Bay Area. Pacific on the left, and there's the bay. And I put some, landmarks. Ames is down by the bottom of the bay. And it's about 35, 40 miles from San Francisco. 35, 40 miles, and at the wrong time of day, 3 hours. And so I put some landmarks around the area. They say geography is destiny, and there's a lot happening that's in this area. The south end of the bay is what's known as Silicon Valley. And if you look down in that area, Google Ames actually leases out a plot of land on its federal property to Google, and they're building this massive Google complex out there. It really is. It's just looks like a big circus tent. It's something to see. Apple built its famous spaceship in the Cupertino, which is less than a mile from my house. Stanford is just up the road. So a lot of the universities in the area, there's Stanford right up the road, UC Berkeley up a little bit north of Oakland. There's UCSF, UC Davis, UC Santa Cruz, San Jose State. These are the local universities. And then some of the sports teams in the areas, just so you can kind of connect the dots. You know, the A's are playing in Oakland. The Golden State Warriors used to play right next to them, but they moved across the bay. And now the Giants and the Warriors play in San Francisco. The 49ers moved down from San Francisco to the South Bay, and they're just down the road from Ames. So that's kind of the geography of the area. It's a very busy area, lots of traffic, lots of people, expensive housing, but there's a lot going on, from a technology perspective. This is a view of Ames Research Center, an aerial view. It has its runway. That runway used to be an old Navy base, and now it's part of the Ames facility. I'll talk about the structures of there, some of the big test facilities, but the one that sticks out is the big wind tunnel that you see there. It's the largest subsonic, well, it's the largest wind tunnel, and the largest wind tunnel is going to be subsonic. We do parachute testing in there and all kinds of full-scale testing in that facility. There's roughly 2,000 people, 2,500 people on the base at any given time, non-COVID, when we were allowed to go on base. The budget's about $1 billion. And as I mentioned earlier, Ames is one of the early NACA laboratories. And so it started in 1939, and the story goes Langley started first, and then it was purposely designed to have another research center that explored contrary ideas to what was happening at Langley. I mean, it was purposely thought to set up kind of a West Coast alternative thinking kind of approach to aeronautics. And it's not to say we were, contrary for the sake of being contrary, but it was to get a different group of people and different researchers that weren't just grooved to one groupthink, again, by design. And that ethos kind of persists with us today. Ames' reputation is one of being a little, thinking differently, sometimes contrarian, and it fits right in with sort of the Silicon Valley ethos that we experience here. And there's some cool pictures from, back in the day when the laboratory was formed. So we've been around for 80 years. I'm not going to go through every little insetted picture here, but, some of the cool stuff that's come out of Ames over the years. The one that I'm most familiar with is the blunt body concept, because that's my area. That was a H. Julian Allen invention here at Ames Research Center, which was contrary to the thinking at the time. If you go back to getting faster and breaking the sound barrier and going faster and faster, everything kept getting sharper. The aerodynamic surface is sharper in order to reduce drag. But then the heating started going up really, really high on these sharp aerial vehicles, to the point that you just couldn't have a leading edge surface that would survive the heating environment. So it became time to say, well, how are we going to take people from outside of orbit and re-enter safely? How are we going to survive that heating environment? It turns out, in a counterintuitive kind of way at the time, a blunt body actually gets you down there and manages the heating. So it works, pretty well in both directions, because you want to slow down coming from outside from orbit, from outside the atmosphere. So blunt slows you down, and also it manages the heating. When that was discovered, it was, classified, and, that was going to be the secret of how that came about. Some other areas, I'm going to pop up to Kepler, because that's kind of the most recent. That was an Ames mission. Bill Barucki was an Ames scientist who had this crazy idea that we'll put a telescope in space and we're going to stare at the sun and a star, and what we'll do is we'll count photons, and every now and then the photon count will dip, and that must be because a planet around that star must have occluded the view, and we'll get a dip in the photon count. But that dip is a very, very, very small percentage, and the precision on these things is just amazing. And he was rejected, said there's no way to do it, and he persisted at it, and we finally got Kepler out there, and Kepler has really revolutionized our thinking of the universe. It was suspected before Kepler that all those stars out there might have planets. But Kepler has shown that, yeah, not only is it suspected, but they're even more abundant than we thought. The number of planets out there really, really is abundant, which has meaning for, what's the potential of life. So I want to move on from that. A lot of exciting things over the history of Ames. I want to talk about what we do at Ames, because each center at NASA kind of has what I'm going to call here core competencies, which is their areas of expertise in the areas that they really lead for the agency. So for Ames, I'll just kind of go through here. One is air traffic management, which is the air traffic management system for the nation and really the world. This is a very mathematically heavy kind of activity because you're doing all these network analyses and trying to get throughput through the airspace in the models of air traffic. Right now, the big challenges are all the UAVs and all the little delivery drones that we have out there. How do they fit into the airspace? How are they going to talk to each other? How do you assure safety? It really, really is a big topic. The next one is entry systems, which is the area that I come from, which is how to get from through an atmosphere and land on a surface. We do a lot of advanced computing and information systems. The supercomputers for the agency reside at Ames. We have a quantum computer that we do some work with Google on. Intelligent adaptive systems is really about robotics and autonomy. Cost-effective space missions are various space missions, including small sat. So we do a lot of small sat work. And in fact, we do some small sat work with UF, and I think I have a slide on that. Our traditional core from the very beginning from Monaca Center is aerosciences. So it's, aerodynamics, controls, aircraft design. We also do some sciences, astrobiology and life sciences, and then space and earth science. So it's a very diverse portfolio. A lot of, research centers. I mean, it's a lot of smart people, but it's also a lot of, really fantastic facilities that enable you to do the discoveries. Like I said, the big NFAC facility sticks out, and that's the Mars parachutes right there being tested in that facility. It's a huge test section. You're dwarfed. I mean, you stand in that test section. I've actually stood by the test section while they're running a test, because it's so big they don't care that you're poking your head into the test section while the air is going by. We also have some transonic tunnels. For the entry systems, a marquee facility is an ArcJet complex, and that is basically you take a tube of air and you essentially shoot a lightning bolt through it that supercharges the air that you then put through a converging diverging nozzle to supersonic conditions, and then that gets very high enthalpies and heat content so that you can mimic what you're going to experience coming back from space. It takes a city block to really operate this facility, between the power that it takes and the management of the vacuum chamber and all the associated equipment. We have a range complex, which is a ballistic range, an evacuated ballistic range, kind of in the middle there with a kind of a red glow. So you would shoot a projectile down through that evacuated chamber to get to other planetary conditions. You could put in CO2, for instance, which is how we mimic the Martian atmosphere. And then you take photos of the object as it flies down the range. And then based on how it flies, you then back out what the aerodynamics of the object must have been in order to have flown the trajectory it flew. We have some flight simulators, supercomputers, and then the upper right is a big hyperwall is what we call it, which is, a series of screens that are all tied together that you get this, massive view on these massive simulations of, galactic formation or other science activities. Okay, we also have some going flight projects, and as chief engineer, these are the things that I'm most interested in, and I'll touch on them very briefly. One is Viper, and that is going to be a rover that's put on the moon on one of the poles to basically scout for water. So it has instrumentation that's going to look for volatiles and determine what is the ice content at the poles where we expect it's pretty high. This is really an amazing engineering challenge because we'll be live driving it. It's not an autonomous vehicle, and the key is that you have to stay. It's at the poles. So think of being at the poles at wintertime here on Earth. You get this low horizon sun, and you also get a low horizon Earth. So you're essentially driving around trying to stay within view of Earth for calm while also staying in the sun for power. And if you don't do that, you could basically get caught, either out of calm or in darkness, and your vehicle freezes. So that's what we're working on now. We're also flying a Sophia aircraft, which is an airborne telescope. And the idea there is get above the atmosphere, which absorbs much of the the constituents in the air, absorb some of the frequencies of the light that we get from objects in space. So you get above the atmosphere, and then you're flying a telescope, and that's an ongoing activity which requires maintenance on the aircraft, maintenance on the telescope, upgrades to the instruments, and keeping that flying is an engineering feat. Another thing is Mars sample return that is being discussed now. This is being led by Jet Propulsion Laboratory, which is a campaign to bring back samples of Martian rock. And then Ames is involved with the thermal protection system to get that object and bring it to the surface of the Earth safely and with high reliability. The photo there is actually from an airborne observation campaign of the Stardust mission. And that's actually a campaign that I led. That's from an airborne DC-8 as we were tracking Stardust enter over Utah. Then we have another satellite activity, which is Starling, which is looking at swarm technology. So we're looking at swarm comm and remaneuvering of the swarm and repositioning it while in orbit. Here's another one I did was Chomped, and this is with UF. I won't go over the details, but I threw it up there because there's probably students and professors that worked on Chomped. So there is some collaboration that happens between UF and Ames. One going on right now is CLIC, which is a laser comm system, and that's a partnership between MIT, UF, and Ames. So what I'd like to do now is just kind of get into chief engineer and what does a chief engineer do. I can't imagine you're interested that much in org charts, but I just wanted to point out where the chief engineer sits in an org chart. And it's basically a technical advisor reporting directly to the center director. So it sits, pretty, apart from the technical organizations, the functioning organizations, and is an independent voice on what's happening technically at the center. So, my boss is the center director. It's the head boss there, and I'm not beholden to any other project or any other org director. So my function and the reason they have chief engineers is really a governance idea, which is to say, when projects are being executed, the project manager will make decisions based on schedule and cost and some other factors. And there needs to be a voice in there that is speaking for engineering that says, hey, this is the right way to do it. These are the risks. And, this needs to be included. And so it builds in an alternative voice and an alternative opinion that needs to be adjudicated. You can dissent from the project decision on what to do and then have it adjudicated, which is a governance issue. And actually, if I can just step back on that, that construct fell out of the Columbia accident investigation, which was, decisions on whether to inspect the heat shield on the shuttle before reentry, and the decision on what engineering data to acquire needed to be debated, not just dictated from a program side, but also from inline engineering, and that's a governance issue. So what's the chief engineer do? Formal technical authority, and that may not have a lot of meaning, but what that says is when you're going through an engineering system, there are a set of requirements and standards, and the requirements and standards, the engineering requirements and standards for the systems ultimately have to be approved by me. And so if there's a dispute about how they're going to test or how they're going to verify, or what margins to put in, ultimately I have to sign off on those. Now that doesn't mean I go take every project and do requirements. That's not what I do. There are people doing that, and then I check in with them, and then if there's an issue, then we both adjudicate that together. So that's how it works out. So that means I'm involved in all the projects at the center. You set engineering policy, anomaly resolution. If something happens on a project, in fact, I'm doing one right now where we have a test anomaly, and what do we do with the test article, and how does it impact on schedule, and what are the risks? These are all being parsed within my office. And then there's risk identification, both for individual projects and systemic risks across the center. What are we seeing, from an engineering process across the center that we need to improve on? So what's a chief engineer like? As I mentioned earlier, it's a large scope spanning multiple projects and disciplines. You got to shift gears frequently because, a lot's going on, and you saw the diversity of activities that are happening at a place like Ames Research Center, and you're popping across all of those. Because you are, you rarely are you the expert in any particular discipline. So, you've got to learn, you got to have some instinct for when things don't sound right. You got to have, decent fundamentals about, physics and engineering. So when you sense something that's just not hanging together, to ask a question and ask the right question. And you have to learn to rely on the experts and get from them the information that you need. You're also spanning across, you're the go-between between the project all the way to the center director. So you got to communicate, at a detailed level with the working engineer, and then you need to synthesize and distill what you've learned and then communicate that to high-level management. High-level management are also engineers. It's not like they don't have the background, but they're executives, and you need to distill it down and give them the essence of what's happening. So it's that being able to communicate at multiple levels is really important. And then the final thing, it's like location. It's balance. Cost, schedule, system capability, and risk. You're always trading those in the system. Okay, I also like to, you saw all the NASA centers across the country. It used to be each center ran its own internship program, but I think they've recently consolidated all that. It's one interface now, www.intern.nasa.gov, and you can go and see what internships are available at any center, including Ames. Ames has a history of bringing in a lot of interns over the summertime. This is pre-COVID. I think once we come out of COVID, it'll happen again. There are virtual internships happening. So if you're interested, I still encourage you to go to the website. The Bay Area is very expensive, so it's tough to come out as a student in the summertime. But for a while there, we had some on-site housing that was left over when the Navy was there. So it was old Navy housing that we converted. And so we were able to house many of the students, which really enabled, we pull in interns from all across the country. So if you're interested, go to the website, give it a look. They're competitively selected. So, we do get a lot of applicants. Okay, so what I'd like to do now is, hey, that was my pathway to NASA. It's not like I graduated and said, oh, I want to go work for NASA. I just knew I wanted to go to graduate school. And then I was fortunate enough to get a NASA, grant, which led me to an internship at NASA, which then led to a job eventually later on. I never thought I'd be in California. That's not something that ever crossed my mind. But, I just kind of flowed with the opportunities. And so that's my closing thought here of how do you go from UF to NASA or to any place else, really, is be open to possibility and opportunity. What's an engineering job like? I can tell you there are so many different types. I mean, engineers go into finance, engineers will go into executive leadership, engineers can do research, engineers can, build things. There's a lot of possibility and opportunity, and you just have to open yourself up to those. Some other thoughts is be comfortable within a team and learn to leverage group intelligence toward managing complexity. I mean, the world is increasingly complex. The world is increasingly interconnected. And the complexity is such that, one person can't possibly be an expert in everything. Well, maybe it's possible, but this person cannot be an expert in everything. And so you've got to really be able to work within a team and leverage that group intelligence to be able to manage that complexity. And I think I see a lot of that now in undergraduate and even graduate school of, group projects and things like that. And that's really important. How to get along, how to get the most out of your teammate. And then I also have, be reliably competent. I think I have a title of chief engineer, but if I think of myself and I say, does that mean I'm the best engineer at Ames Research Center? You know what? Absolutely not. I'm not the best engineer. Any number of engineers where I just, I talk with them and I go, man, that is just really, really great. I don't view myself as the best engineer or, maybe even the top 10% or something like that. Not that you ever rank them. But the idea is to be reliably competent. If you can get a job and people trust that you can get the job done and get the job done within cost or schedule, or, if something goes wrong, that you can honestly bring forth those ideas, it takes you a long way. Everybody in the world doesn't have to be the best engineer as if we can rank the best engineer, but this notion that you need a team of the best people in order to achieve, great things, it's really not true. You just need to be reliably competent and you can achieve really fantastic things. A sub part of that, though, is, be mindful of derailers. And this is very personality driven. I think people in any industry will tell you this. Some people can have a fabulous skill set, but they have something that whether it's a stubbornness or a blind spot or, some kind of professional character that can really derail them. And you can just get sideways with it. And so, no one's perfect. You're going to have some skill that you're not really great at. Just don't let it be so bad that it sucks you down. So, be mindful of that. I'm pretty good at these areas, not so good here, but don't be so bad that it drags you down. So, be reliable and be competent. And then the final thing that I see in all areas is to be curious. That's what really leads to change, to understanding, to new ways, and also your own engagement. If you're in a class and you got to learn this thing, it's like, oh God, I got to learn this, and whatever, it's some equation or something, you got to plow through it. It gets tough, right? It just becomes a grind. I got to do it because I want to get the grade and I got to understand it. That's so different than if you're just curious about it and go, hey, how does this work? And all of a sudden it's not work. You're just naturally curious about it, and it doesn't feel tough. So, there will be times you have to grind. Even in a job, you have to grind and just get through it. But what I've seen is, if you can be curious and ask, why is that? Why are we doing it that way? How does this work? All of a sudden you start asking the right questions, and advancements, really happen. So nurture that curiosity is my message there. All right, boy, I tell you what, that's 38 minutes of no feedback discussion in one way. It's a heck of an experience for me to be able to talk like this. I guess I will be quiet now, and then we turn it over to some Q&A. For those of you listening now, thank you for your time. And for those who are going to watch this later, hey, thanks for listening. Ellie, back to you, I think.
Yeah, thank you so much, Dr. Kontinos, for that great presentation. It's always so exciting to see the amazing things that Gators can accomplish. So now, we will take some questions from the audience. Feel free to put them in the YouTube chat, and I will read them out to get an answer. We already have our first question from Olivia. It says, how did your master's degree shape what you wanted to do once you graduated?
Yeah, I got to tell you, I was always fascinated with aircraft, and in particular fighter jets. I mean, fighter jets are so cool. There's nothing really to say about that. And so when I was applying to graduate school, when I was a co-op, the F-16 was in production, and the work was, it was a redesign of a radome on the nose, and it was very small scale, and it wasn't big enough for me, if that makes sense. And so that's why I went to graduate school. And then it was just, I saw this flyer for hypersonics, and I was like, well, hypersonics, that's even better than aircraft jets. I mean, that's, Mach 5 and above. And I don't know, it has some sexiness to it, I guess. And so I got into hypersonics, and that really set the mark. That's where it came career, computational fluid dynamics for hypersonics, high-speed reacting flows, which then led to entry systems and understanding thermal protection systems and materials and shapes, and it just kind of opened from there.
Great. We have another question from Dr. Miller, and he says, what advice do you have for our students who seek to join NASA or any other aerospace organization?
I think I mentioned two things that I'll reinforce. One is, again, follow the job, be prepared to move. It doesn't mean you have to move. You're in the Air Force and you move every 2 years, or in the military. I know they do those things, and those families are just amazing to me. But you got to be open to, hey, here's an opportunity in this part of the country I've never been in. I'll spend a few years there. And in particular, NASA, NASA does a lot of outreach with students, and go to www.intern.gov and see what's there, and follow that process. That's the best way, is to get in as a student. And then, NASA does hiring. There's multiple hiring within NASA. There's working properly for the federal government, which is what I do. I'm a civil servant. I work for the U.S. government. But all the NASA centers also have a contractor workforce that's on site. You're working for a private company, but you're doing NASA work on site. And that's another entrance area. NASA has needs. You work through your professors. NASA's not shy about the things that they need. At Ames, we need systems engineers, we need project managers.
We have a kind of follow-up question from Justin, and he asks, how should people are searching for intern or full-time positions, how should they make themselves stand out on their applications in order to get jobs with NASA?
Oh, wow. Yeah, I don't know. I wish I had a good answer for you. It's highly competitive. I would say enthusiasm counts for a lot. I think, hey, here's an area I've always been very interested in, blah, blah, blah. And let's just say in real life, you're interested in 10 different areas. I don't know, maybe you got, varied interests. When you're applying to that one, say, man, I've always wanted to work in air traffic management. Go ahead and say it.
Great. Dr. Dixon has a pretty similar question to what I had myself. And he asks, what would you say are the next big technology frontiers and growth for NASA?
From a technology or from a mission standpoint, what do you like? Where are we going, or what are the technologies to get there?
He specifically asked technology, but I'd like to hear both if you have an answer.
Yeah. Give me a second to think through this.
Yeah, of course.
I think technologies related to in situ research utilization is going to be important. So at the moon or at Mars, to be able to use the resources that are there for either generation of things for life support, oxygen or fuel, but also converting these things into building materials or for 3D printing, being able to use materials there to be able to 3D print your parts. That's going to be a really important area. Another one that Ames works on is autonomy. And so really, if you think about the operations that happens now about, let's say, the International Space Station, the International Space Station is, within direct comm, no comm delay. You can call them up now and have a conversation. And you don't have that time delay. You're at Mars, for instance, you're 7 minutes away, from a comm. You're not having a conversation. And in fact, I think they've shown that a delay time for as little as 4 seconds really can obliterate a conversation. And you've experienced that yourself, where even on Zoom or a phone, you get that 3-second delay and you say, you want to go? Okay. All right, you go. Right. And all of a sudden you can't have a conversation. Okay. Imagine 7 minutes. You're not going to have a whole bank of engineers on the ground problem solving. You're going to be alone real time. And autonomy and human machine interaction and how that's going to work out is really a big research area if you think operationally how that's going to go down.
Yeah, that is a very interesting frontier.
Yeah, and then Ames, this is maybe an Ames perspective, life detection is fascinating, right? I mean, how do you detect life, apart from it coming up and biting you, which is highly unlikely, right? I mean, if we find something somewhere, it's not going to be so apparent that it's going to come up and bite you. And you're going to have to do it remotely and autonomously, and how to get that done. It's very much a lot of chemistry, things like that of figuring out how to do life detection. What begs the question, well, what is life? And how do you detect it, and what are the processes that aren't just chemical but actually constitute life? Another fascinating area. There's so many, right?
Definitely.
Yeah.
From Dr. Banks, he says your role is fascinating and that it seems like much of your activity is in an adversarial role advocating for engineering. What advice do you have for students to prepare or practice for these kinds of skills?
Yeah, that's a great question. Thanks for it. And it's not adversarial per se. It's potentially adversarial though. And so you really have to have a sense of how do I move the organization forward? How do I move a project forward? How do I get folks to think differently about this? And so you can come in and say, hey, I'm chief engineer and we're going to do this. Well, that only gets you so far, right? At some point, people stop listening to you because you're just there. So at some point, you're suggesting, some point you're nudging. It really is, you have to kind of have a sense of what's the best methodology to achieve an outcome. And it's not always a hammer. Sometimes it's finesse, and you don't always get it right. You gotta read the situation and read people. And that's what it is. And it helps because of the governance is, I always said there's the nuclear option. The fact that you walk in and, you have a nuclear option that, that's the chief engineer. And if the chief engineer really is kind of torqued off about something, it can create problems for me. So people naturally kind of want to listen to you a little bit, even if they don't believe you. But you don't utilize the nuclear option, right? Don't set off the nukes, because you can only do that once, and then from there on out, it becomes ineffective.
Very true. From Anthony, he asked if you could elaborate on the development of entry systems, such as new materials or technologies that make reentry safer.
Yeah, thanks for that too. It's an area I come from, so I love talking about it. So we actually have a new material line for thermal protection materials. Now, people say, hey, the shuttle comes in, we got a thermal protection system. It just works just fine. Please appreciate that the heating rates that these different vehicles experience are orders of magnitude different. So the space shuttle on, let's say if you're sitting in the sun, I think the sun irradiance to you is like 0.01 watts per centimeter squared, something like that, something less than one. An oven, if you stick your head in your own oven, I think it gets into single digit watts per centimeter squared. The space shuttle coming in on its belly, the flat surface is like 20. The leading edge is like 70 watts per centimeter squared. And that's what we had to burn through on Columbia. I mean, it's these materials have to have shape stable materials in order to maintain the aerodynamic qualities of the vehicle. When we fly into Mars, we're in the 200s-ish of watts per centimeter squared. When Orion, which is being built now, but think of Apollo, when they come back from Earth orbit, they're on the 800-ish watts per centimeter squared. Stardust, when it came back, is 1,000, 1,100-ish watts per centimeter squared. Mars sample return, because it's on a trajectory that's coming back pretty hot, it's going to be in the order of maybe 1,500, 2,000 watts per centimeter squared. When we sent a probe into Jupiter, it was order 10,000 watts per centimeter squared. So, I mean, these are huge orders of magnitude, which require different solutions. At some point, you get from a shape stable solution to what's called an ablator, which is essentially you're consuming the TPS material in such a way that's taking away the heat of reentry. You're basically burning off the material. And that process of burning absorbs energy and also flows some of the energy away from the spacecraft. So we're using a new ablator on Mars sample return, which is a woven material, which is fascinating, right? We take a big loom and we're weaving combined threads of carbon and phenolic, which is a typical high constituency of a material for ablators. And you weave it in such a way and then infuse it with other materials that give you very, very high energy managing potential. This weave technology is used in composite parts in the aircraft industry. So it's really come along, and NASA has leveraged that advance in technology to roll it back into ablators.
Very interesting. Also from Anthony, he wants to know what the most rewarding project you have worked on is.
I will say, I'll change the question. not necessarily rewarding. I will tell you some cool NASA moments where you just sit there and I've said, man, how did I get here? What draw me here? And I think one was, there was a Mars landing. It was Mars, the MER rovers, and this must have been late 90s. And I was at JPL, part of the entry team, and was there. And the rover had landed, and they started, sending down pictures from Mars. And there was a room off to the side that they were just kind of throwing up the pictures, from Mars. And I'm sitting there looking at this, and I'm thinking to myself, what am I, one of 15 people here looking at this that has never seen this before? I'm like, one of 15 people that has seen this for the first time. It was just mind blowing to me. It's like, no one has seen this. It's just right there. We just landed this thing. It's taking pictures, and the world, we haven't released it yet. I'm like one of a handful of people that has seen this. It just blew my mind. Similarly, when Stardust, I was involved in the post-flight analysis of that heat shield. And we cored the heat shield, which means we basically took a plug out of it, because we're going to look at how the material performed to validate the models that went into designing it. And the heat shield, I think, was at Johnson, and they cored it and they sent it to me, and they delivered it to me, and it's sitting on my desk. So I got these cores from Stardust. I don't know if you know the Stardust mission, but it was a sample return from a comet tail, and it went way out, I don't know, millions and millions of miles. Took 7 years to get out there, and another 7 years to come back, or whatever it was, to collect this cometary dust. And here it is. It came back, and I've got this core from this device. I'm thinking to myself, what's the definition of foreign and alien? I mean, if you go back to think about like stamp collecting, I doubt anybody collects stamps there, but back when stamp collecting was a thing, it was because the world was big, and you looked at a stamp and you said, "Man, I came all the way from Indonesia." You're kind of blown away. Holy crap! I had this stamp from sitting on my desk. It's on my desk. I mean, it'd been out millions of miles. What's it doing on my desk? Is there anything on the face of the earth right now that is more foreign and alien than this thing plopped on my desk? I think not. How did I get here?
It's got to be very cool to have a piece of space sitting on your desk.
Yeah. And what's really great is the Stardust heat shield and that body is actually in the Smithsonian. And they covered over the plug so you can't see it. And they arranged it such a way that if you go to the one on the mall in DC, and you can see the Stardust heat shield there. They covered over. But if you get down on the floor and look up, you could kind of see where the hole was. So I'm in the Smithsonian, right? And I get, people all around, right? It's a museum. And I get down on the ground, I'm looking at it, I look at the hole, and then all I want to do is go, hey, hey, random US person, come here. I made that hole.
Great travel tip for DC next time.
Let me tell you, nobody cared.
Kevin asked, he says, going back to when you decided to go back to grad school from industry, did you plan to study hypersonics? And what experiences in the industry helps you decide on what to study?
I think, again, it was happenstance, right? I was applied to a couple graduate schools, and NC State happened to have a hypersonics program, and I just caught it, and I was like, I wasn't looking for hypersonics. It just pulled me in. So nothing in particular from the experience that I had as co-oping that said, okay, I want to do hypersonics. I think the experience from what I got from co-oping was, I don't want to design or be involved in just this sub-assembly. I want to look at the whole airplane. And I didn't want to look at the whole airplane. How do we design airplanes? Why are we designing airplanes the way we do? Right? I just, I had a natural inclination, and that naturally takes you to graduate school. You got to have a desire to say, I want to attack the bigger problems.
Makes sense. Philip asked if you could expand on the role and the future of 3D printing in both normal fabrication and as a tool for spacecrafts.
I'm sorry, ask the question again. I'm not quite sure what the intent was.
Yeah, if you could talk a little bit about the future of 3D printing for normal fabrication or as a tool on a spacecraft. Philip is curious of that.
Yeah, it's not really my area, but it's it's easy to imagine the future when it comes to 3D printing. I mean, I will just say, imagine your house. And, my refrigerator right now has, the water dispenser doesn't work there. And I don't know the part that's broken in there. And I got to call Sears, and it's going to cost me $80 just for the guy from Sears to walk in my front door before he's even looked at it. Hey, I'm going to get that part and I'm just going to download the file. It's going to come to my garage. I'm going to have a little printer right there, and I'm going to print it out, and they give me the directions to how to install that thing. I mean, it's going to happen on Earth where, just-in-time delivery changes from someone made it for you someplace else and put it to your doorstep to, hey, maybe I have, rudimentary or some level of manufacturing capability right here in my house, and they're just nailing me information, and then it just pops out. All right, now, they have to have different qualities, and, for consumers and things like that, the quality doesn't have to be great. Maybe you just make another one. That notion of convenience on Earth becomes necessity when you're off Earth, right? Because you just can't you can't get there just in time because, getting there is tough. And of course, you can't provision it because, mass is money. So if you can provision just the raw substances, and then just beam information, then that logistical nightmare that you have changes completely. Now, the problem that you have with this is, can you get various material qualities, and what are the different constituents that have to go into when you're 3D printing, and then at least for from a process control standpoint, how do you assure the integrity of that part afterward? I mean, do you X-ray it, and can you X-ray it? And, how do you do non-destructive evaluation? I mean, those sort of quality control things start creeping
in. We have another question from Anthony. He asks, how close are we to reaching a fundamental understanding of turbulence?
I love that question because I know people that work in turbulence. And I say, what is that? The ultimate job security? Right? I mean, I work in turbulence. You got solved yet? No? Okay, you're still working. There's my flip answer.
Okay. Derek asks, is there a possibility for a research project to come out of an idea or invention?
Oh yeah, absolutely. I mean, we build that into the systems that we have within NASA. Ames is a research center, so we have, funding profiles that people compete to advance their ideas. So they'll propose, and it's internal research and development funds, and there's a lot of competition within NASA itself on various ideas and how why does NASA do what it does technology development wise and things like that. And some of it's top down. Here are our needs, and you kind of in a very requirements driven kind of way flow down. But a lot of it's push. It's push technology of people have some interesting ideas. Sometimes it's solutions looking for problems and they connect. Sometimes it's solutions that you're not quite sure what problem is going to solve. But people push their ideas and compete within NASA for funding.
I have a question myself. So I wanted to know if there's anything that you've learned within your time in industry that schooling and education just completely did not prepare you for.
Well, I don't think there's anything I was completely unprepared for. That I can't. I can tell you areas that I was underprepared for. How about that? And I would say most of that is personal dynamics. How to interface with people to get these sort of. It's not necessarily leadership, but it falls in the leadership qualities, right? I mean, you don't necessarily have to be the leader that says, okay, whatever the leadership model you have is, you're the leader. No matter what you do, you're going from environment to environment where sometimes you're a leader, sometimes you're a follower, sometimes you're a pusher and a puller, and understanding your role and appreciating what people are trying to get and get the most out of people. They don't teach it for you as an engineer. And maybe I'm being too stereotypical, but engineers kind of, as my wife says, Dean, just because it's true doesn't mean you should say it. Well, but it's true, right? I mean, what am I, right? Engineers are kind of, truth driven and, kind of have these antisocial, skids to them a little bit, as a general rule, not universally. But doing that. And I think the other thing too is, I think coming out of undergraduate, not necessarily graduate school, because graduate school forces you to do it, but writing, knowing how to write efficiently and to the point and clearly. And that's an important skill that serves you well. Even in email, being able to write email clearly I think is an important skill. And so that your message is communicated appropriately. So they're not technical. Let me think technically. Systems engineering, I think I didn't get much systems engineering and understanding how it works and the process of building a system, and from requirements management and requirements verification and integration tests and how all that kind of goes down. You don't really have a feel for it, I think, as coming as an undergraduate, right? You kind of do these projects and, I got my buddy and they're going to do this part of the project and I'm going to do this part, but you don't really get into really hardcore systems engineering that steps back and says, okay, what are our requirements? What are we doing here?
Okay.
But so, you can't learn it all. But I would just say this: you can't learn it all as an undergrad, right? It takes a lifetime. So give yourself a little bit of grace, and just absorb, along the way, and all these things will come in time.
Yeah, great advice.
If they come.
Thank you. So at this time, our presentation and discussion will come to a close. I want to thank everyone that attended for asking questions and staying engaged, and of course, thank you, Dr. Kontinos, for giving this great presentation. Please be on the lookout for the next episode of the MAE Speaker Series, and I hope